All right. So, how you guys doing today? Good. Perfect. All right. So, I know it's also a bit of a. I'm still working on the syllabus right now. But there's certain things that I decided on the syllabus. So here's something I can tell you. So I talked to the St. Louis company, right? And they told me that they could possibly transfer uh, the ones you already had in the Dr. Domains account to me. So I think you can keep that for the semester. I'll try to send you some announcement when I get those all information. So you'll be able to continue on the same gauge homework. But do not worry about the homework was due like yesterday, right? Don't worry about it because seriously, I don't even know what that is. So I'll try to make a new one later. But you can keep it. I think you can keep it for the your online homework. There will be some other. So besides the same gauge, I don't know if it's spelled the right in the company, but besides the same gauge, there'll be some online assignments, but there will be actually your chance to get some more extra credit. So it's not really required, but it's really good to do. It's optional, but you can get some extra credit. So this will be your part of the homework. But whenever I ask you to do some additional online homework, that will be your extra credit. Okay? So you can do a lot with the same gauge, and maybe later this semester we'll do some online homework too. And then the exam, I think this is also quite important information here. Exam will be done in person. So there'll be no more online exam this semester for midterm. Unfortunately, we have to do something else for final, which we don't have a class after Thanksgiving. You guys know that, right? Okay. But midterm, there'll be two midterm. Do you guys see my first one? So there'll be two midterm. Okay. There'll be two midterm exams. My guess is now the first one will be at the beginning of the October. The first, maybe, beginning of the October, we're gonna have a first midterm exam will be there. At the beginning of October. So what happens is this one. This will be done in person. So in the maybe first week of October, for example, we are in group 1, Wednesday, B, right? So the week of maybe, I think there was it's October 4th or 5th, okay? And then that week, you don't have to come on Monday. You only need to come to Wednesday to do exam, okay? And those two other part students will come on their Monday and Friday, will do the exam. So during that week, there will be no lecture video posting because the other 2 days, the other two part students were taking exam days. So only thing you have to do is I'll post this the week of, probably beginning of the October. Are you on Wednesday? That week, there'll be no lecture video posting, but just prepare your exam date, which is on Wednesday in here. So this will be only like 15 minutes long. The other will be kind of not done, sort of thing. But this is quite important for this part of the organic chemistry. So this is something, didn't want to draw, right? Conjugate acid, conjugate base. So for example, this is a strong acid here, HCl, right? It's a hydrochloric acid here, right? And this can go like this, okay? Or you can say, or still lowering. Either this way, okay? They're the same thing. This is our Arrhenius definition we didn't talk last time. This is slightly more like definition here. So, but either way, it tells you what? It shows you some like protons there. It's hydrogen cation, which is what? Simply same as protons. Okay. So whenever you talk of the acid and base, most likely it's just about which one has more proton or less. Or in Lewis, it's also the same thing, but they do it with the electrons, because the electrons and the proton is kind of a concept. So does it make sense, right? So, but in here, which this is a strong, this is strong acid here. Okay? This is why there's only, I guess, this one. So we don't consider this one. We don't consider reverse reaction or anything because it's a strong acid here. Then one thing I want you to remember from here is this one. Whenever you have a strong acid compound, strong acid, that means they're going to fully dissociate into these two forms. One of them is protons. And this is strong because, ironically, these two has weak bonding. Okay? So sometimes it kind of confuses you. So that means weak acid, okay? Weak acid like this one. Okay? This one, or you can say this one plus water. Oh, so this is the weak acid, right? And this is the weak because the bond between these two is stronger. So think about it, that kind of makes sense. Whenever you have strongly bonded each other, they don't want to give out the protons. So by definition, strong acid should donate a lot of protons. But this would do it because they have a weak bond. But if you look at these two, this one is something you can do. When you look at the fluorine in the periodic table, where is it? Look at the periodic table, where is it? It's on the second row, right? So this is, relatively speaking, small, and also electronegative, quite strong electronegative. Then if you have something that is hydrogen next to it, the bond will be, relatively speaking to this one, a lot stronger. So stronger bond, ironically, makes this weaker acid. So it's always the other way. The bonding acidity is the other way. But sometimes it kind of makes you confused because you almost feel like if you have strong acid, it also should have strong bonding too. But it's actually the other way. Okay. So this is something I want you to remember before we move on to chapter 3. Okay? Does it make sense, right? We good? So here's the reason why in the textbook you're now talking about some numbers in numbers for Ka. Okay? Ka is simply some the rate constant that is your about your acidity here. So this is what we call Ka. And later time, they actually often use not just Ka but pKa. Okay? So here's the thing. Ka is rate constant. Simply means it tells you about the relationship between the rate and your molar concentration of reactants here. So if you have a higher Ka value over here, that means most likely you're going to have somewhat faster chemical reactions over there. But if you put the pKa, the p value is simply means negative log of something. So this is a negative log of Ka. That's the pKa. Okay? So that makes the pKa. So that is a negative here. So if you have a lower number for your pKa, that means it's a higher in Ka. So lower pKa means what? Stronger acid. Okay. So this is something I want you to kind of remember. Okay. So it makes sense, right? This is a Ka value, but we're gonna put the negative log. This is why the lower K will mean the strong acid here. Okay. So this is why sometimes those pKa value will be given for each acid or base. So you can do some problems like this. Okay, so maybe I can give you one. Okay, this is one that interacts with OH minus, which is a hydroxide anion. That makes anion of acetylene here. Okay, plus water. Okay, so here's the thing. Whenever you see something like this, you always assume, unless it's very strong acid or base interaction, you also need to think about both ways. This is not going to be dominant on which side unless it has a really different in pK value. So pK value for this one, acetylene here, is about 25. And the water is, pK value is more 15.74 right here. Okay. So if you look at this one here, it seems like they're going the both way. We can tell which one will be dominant by seeing the numbers for pK value for this one and this one here. Okay. So what you can do is this one is kind of behave like what? Obviously acid here. Okay. And this one will behave like what? Obviously it's OH minus space. Okay. And then, so you see this one, right? If it goes on the other side, there will be conjugate what? Could you guys tell me? Conjugate. So once it's acid, will become conjugate base. This will conjugate base. Okay, perfect, thank you. And this will be conjugate, sorry, conjugate acid here. Okay. But here's the thing. When you look at this one here, you need to look at it as more like in the both way, right? But this pK value is 25, but I just told you pK value for water is 15.74. So which one is stronger? I just told you. Which one is stronger then? Right? Water is stronger, right? So in this case, if you look at this one more precisely, it will be like this. Because this is a much stronger acid here than this one. So this one will be good example of your exam problem on first midterm. So I want you to do this. I want you to remember this one. Okay. This will be on the exam for sure. This is something I cannot miss. This is something you would do in organic chemistry quite many times, quite often. So make sure you guys do this. This is something you don't have to know, but as you can see, the pK value, it tells you which one should be dominant, because it's determined the Ka value. K value simply, or once more, it depends. It also means how fast, the speed of the reaction. This will be more dominant because it's faster. And also, can you guys actually guess why this is bit also lower in pKa, or will be more dominant? You need to think about the. What I said was, whenever you estimate acidity, how strong that acid will be was what? Bonding, right? If it's weaker bonding, there'll be stronger acid here. If you think about water is pretty stable, I see. But this is also even more stable. But also, if you think about the base form of acetylene here, which is very unstable, right? This is something you don't have to know, just for your understanding. And if you think about it, they want to do more on this one than this one, because relatively speaking, they're much more stable this way. Means they have a bit slightly stronger bond in some than here. So they always want to be stable. more stable. So this is something we can confirm by numbers over the pK. Oh, that's for sure. It was the one what's dominant this one. Yeah. Right? Yes, so that's a very good question. So not even just for this acid and base, but for everything in chemistry, that not just the reaction, but in each like atom or molecule, they always tend to move into the much more stable form. As you can see, also in the resonance. Remember, so one part of this on chapter 2 is resonance, right? The resonance structure doesn't have to be equivalent. Means they always tend to be more stable form. I think, but that's a really good question. So make sure it's because of the unfound principle, Alba principle. So do you remember something in Jenkins 1 that all the atom or molecule tend to be in the lowest possible energy status? That's because of that. So one good example I can give you is this one. Have you ever watched the animation named Bee? There's a honeybee's main character doing a lot of fun things for the human. They actually can talk to the human because it's animation for sure. And there's a human asked the bee, "Why aren't you flying all the time? Because you have wings." You know what the bee answered? Bee answered like, "You're human. You have legs. Why aren't you running all the time?" It's tiring, right? So this is the same thing for this one. They always try to keep the minimum stability, so instability, so it can be more stable. That's something they also do in the nature as well. Okay? All right, so just please remember this one. This is quite important. So I'm going to briefly explain. Oh, there might be something you can do just for this one. So like I said, the pKa, Ka, negative log of Ka is pKa, right? So you can actually go the other way by doing this. You can put 10 to the negative pKa will be the Ka. If you remember this one, this is very useful for your information. So maybe your pK value is 25, and you want to find that the Ka of that compound will be 10 to negative 20. Something like this. But this is just for your calculation. Okay, so let's talk about the resonance structure briefly, and we'll move on to chapter 3. Okay, so the resonance structure. One thing I also wanted to tell you about the one we discussed for SMH was the stable form N2. The resonance structure is also quite important because we need to some think about this one as more like a active form. What I mean by that is whenever you have a certain certain type of electrons available in the molecule, like this lone pair, or the electrons and the pi bonds, they can actually move around. They even try to make even much more stable form of themselves by doing the motion of the electron pair, except the radicals, like they only have a one by one, but most likely you're gonna have either lone pair and double bonds. Means what? You have electrons available in pi bonds, and they will do something like this. So that makes all the possibility of each different resonance structure. But we always believe in resonant hybrid for their identity. But we just doing this for making sure we understood each type of resonance structure of the compounds. So I will give you one example here. Okay. So one of the example I found on the textbook was this one. So whenever you have a carbonate, okay, over here, what you can do, I think you did this already in Jenkins 2, but this would be good review for your resonance structure. So what you can do is you always put your first chemical symbol in your formula as a central atom, except the hydrogen. So except the hydrogen, always you put the first chemical elements you see in the formula, chemical formula, is your central atom always. Okay, and then you're going to put those surrounding atoms around it, around the central atom. So we're gonna do this way. Okay. So whenever you do this, obviously it has two negative charges, but as we know already from thinking 1 and 2, the oxygen is more electronegative than carbon. The oxygen will be the one that carries or that keeps those extra electrons. So that means we can assign those two electrons over here, and then we'll do this one. Okay, so you can assign the 2 lone pair here, 3 here. Okay, like this. As I mentioned in the first lecture, the best way to get the formal charge of each atoms in the molecule is to start with this one. You can also follow the formula that you see in the textbook, but I think I find this much easier to count the number for the formal charge anyway. So there'll be 1, 2, 3, 4, 5, 6. But oxygen is group 6 element, so that's good. Your charge here. This one has 1, 2, 3, 4, 5, 6, 7 instead of 6. So it has one more electron. That's why it's a negatively charged. A single bond negative, central carbon. And same, this is also negatively charged. The carbon has 1, 2, 3, 4. This is also your charge over here too. Okay. So the net charge overall in this whole anion compounds will be -2. So this is one resonance structure of your carbonate. So in the textbook, you can always move this around, right? You can move this around, okay? So maybe this one, lone pair, can move down here, right, to make double bond. And then it goes to here, to here, and here, okay? So there will be 3 lone pair here in consequence. So be down, 1 lone pair down, double bond, and down, and there'll be 3 lone pair. So now it will become, this bond will, so this bond will be removed, right? And this will be there'll be 2 double bonds here, and then eventually, there'll be 1 lone pair gone, right? There'll be 1 more lone pair here from the double bond here, the pi bonding. So now it has single bond, double bond, negative charge. And now this becomes 1, 2, 3, 4, 5, 6. Your charge. So charges are not here and here, not here and here anymore. So in this way, you have this one. Okay. So you can have the other one in the same way. This one too. Then we show you, yeah, and this one as well too. Okay, so you're going to have those 3 resonance structure for carbonate anion. So let me redo this one again. I know it's kind of too much. You don't have to know for now for how you can show the movement of the electron pair by the double arrow or the fish hook. You guys, anyway, but whenever you do this, this is what we're trying to. Okay. So here's the thing. But basically, anyway, so basically what you see over here is this one. Central carbon here, and there's just 3 oxygen. But as you can see, they're quite equivalent on those 3 forms. So there will be in total -2 charge that can be possibly on those 3. So what you can do is 2/3. And they do in a hybrid resonance. So this is the real identity of this one. But we only do this to show in certain case and certain reaction, they need to be in one of these to make that reaction going. They can't just do it in this way. Because once they make actual chemical reactions, either making bond or breaking the bonds, this has to be related to the pair of electrons. So that's already decided by this one. But meanwhile, the real identity of the compound will be in hybrid, resonance hybrid, which is this one. You don't have to know how to make the hybrid resonance structure for the exam, but I want you to know how you can move the electrons and see how many resonance structures you can possibly predict. That's something you only need to do. So if you can do this, you don't have to worry about this one. But this is something you're dealing with in reality anyway. Do you know why? So this is better. This is what we see in reality because you need to record some part of Jenkins 1. I also mentioned this in first lecture. The orbital is not the real thing. It's just the imaginary 3D space where we predict using wave function to find the probability of finding an electron in certain space. That's what we do. So it's all about the chance, not the. So even though we put here and here, this is not accurate because we actually truly don't know if there's a 3 lone pair here and here. We actually don't know. We just estimate based on what we have by chance. So if you're truly using the chance to find the electron, using the orbitals around the atoms in the molecule, it is actually better in this way. Because it talks about the real chance. There's no such a thing as -2/3 electron. But it's only possible because it's about the probability of finding electron, not the electron charge. Kind of makes sense, right? Okay. I'll move on. But the bottom line is for your exam, as long as you can do those 3, you're just fine. Okay? You don't have to worry about this one. Okay. All right, we have about 5 minutes. We'll do something we can do, but let's see. Okay. The last part I want to briefly mention before I move on to chapter 3 is the intermolecular force. It's we call IMF. Okay. This is also a very important characteristic of the compounds we cannot miss because they usually determine most of the physical property of the compounds. There are few, so I'm going to tell you some briefly. So that'll be dipole, okay. And also they have some hydrogen bond, okay. And also you have London dispersion force. And so on. So those are the 3 I want you to remember from Jenkins 1 and 2. The London dispersion force, dipole, and hydrogen bond. So the dipole injection is very simple. The reason we covered dipole moments, what's chapter 1, dipole moments, or chapter 2? Anyway, so dipole moments, because whenever you have 2 compounds, there's just some polarity there. This is slightly positive, slightly negative. Among those 2 polar compounds, they can do some interaction because they're dipole moments. So we call this dipole interaction. We care about this one because dipole interaction is, relatively speaking, quite strong. So they actually kind of governs a lot of physical property like melting points, boiling point, or some proton folding and everything. Same thing over here. You remember this hydrogen bond, right? Hydrogen. So either hydrogen interacting with nitrogen, fluorine, or oxygen over here. They're going to have some hydrogen bond. One thing you normally miss is it's not just about hydrogen, nitrogen, oxygen, fluorine interaction, but also that hydrogen also should be covalently bond to either oxygen or hydrogen and fluorine as well. Okay? And then you're going to have a hydrogen bond, which is strongest dipole-dipole interactions. So we call separately hydrogen bond, because this is a lot stronger than regular dipole-dipole interactions. So London dispersion force is the interaction between non-polar. So obviously, non-polar molecule will have the weakest interaction among these three because there's not much in change in the polarity. There's not much of the interaction they can do in electrical potential difference. So there'll be not much of they can do with the Coulomb's law, but once again, this is where we apply some sort of a electron. So electron is always continuously moving and within the molecule. So even though by its chemical structure, they tend to be a non-polar, but precisely speaking, they're not always polar. They're instant in some certain moments. They can be slightly polar because of the motion of the electron. So this is also related to what we talked today. So it's all about the chance. That means even though you have like two atoms which is the same, they share the same electronegativity. And technically speaking, if they bond there, bond is what? Covalent bond is just the sharing the electron in a certain space. But when you split it into half, even though it's AA, non-polar, you only need to know there's a binding electron in here, it will be same, half and half. But it's just chance. That means what? Even though chance is 50-50, you always go there. Chance may not be 50 in reality. So 50-50 is math, right? So most likely, most of the time they will tend to be non-polar, but sometimes it will be slightly higher on this side and this side. That makes this non-polar molecule tend to be non-polar molecule. Sometimes instantly a slightly polar molecule. That slight change over a whole period of time that makes still do some still very small interaction. Kind of makes sense? Right? So I think you guys did it already in Junction 2 anyway. So this is the last one I want to point it out before we go to chapter 3. So thank you guys today. So see you guys next Wednesday.